Assalamu alaikum. I am Nowshin Ahmed. My ID is 221115082. Our presentation topic is diffraction. We are group number 8. Me and my teammates will be discussing on diffraction and wave theory of light, diffraction by a single slit, intensity in a single slit diffraction, diffraction by a double slit, diffraction gratings, and X-ray diffraction. Now I will explain diffraction and wave theory of light. Diffraction of light is defined as the bending of light wave through a narrow aperture such that it spreads out and illuminates areas where a shadow is expected. Geometric optics predict that when a light will pass through a narrow aperture, it will produce a single bright band the same size as the slit, but in reality, we see a diffraction pattern that produces a set of interference fringes. So we can say diffraction cannot be explained with geometric optics, it requires wave optics. There are two main classes of diffraction which are known as Fraunhofer's diffraction and Fresnel's diffraction. In Fresnel's diffraction, the light source and the screen are at a finite distance from the diffraction aperture, but in Fraunhofer's diffraction, it is in infinite distance. The wavefronts are cylindrical in Fresnel's diffraction, but in Fraunhofer's, the rays are plane. Wave theory of light. Sir Isaac Newton proposed that light was made of tiny particles known as photons, while Christian Huygens believed that light was made of waves propagating to the direction of its movement. When he was asked about the medium, he said it is ether medium. We cannot see it or feel it, but it is there. In 1678, Huygens proposed that every point that a luminous disturbance makes turns into a source of the spherical wave itself. The sum of the secondary waves, which are the result of the disturbance, determines what form the new wave will take. This theory is known as the Huygens principle. With this theory, Huygens successfully derives the laws of reflection, refraction, interference, and diffraction of light. Now my fellow teammate Nayeeb will continue from here. Thank you.
Assalamualaikum, this is Nayeeb Qureshi. My ID is 221115097. I will talk about the diffraction by a single slit, locating the minima and the intensity in single slit diffraction. In the single slit diffraction experiment, we can observe the bending phenomenon of light or diffraction that causes light from a coherent source to interfere with itself and produce a distinctive pattern on the screen called the diffraction pattern. Diffraction is evident when the sources are small enough that they are relatively the size of the wavelength of light. Now we will generate a formula for all the minima in single slit diffraction. Let us take a width of the slit is A. The distance between the slit and the screen is D. Some of the diffracted lights interfere constructively, which is bright spots called maxima. Some of the diffracted lights interfere destructively, which is dark spots called minima. Theta is the angle between the ray R2 and central axis. Now we will split the slit into equal two zones, ray R1 from the beginning of zone 1 and ray R2 from beginning of zone 2. Interfere destructively at P1, which is first minima. To interfere destructively and to create a minima, the path difference between two rays must be half into lambda, which results in the out of phase between two rays. Let's consider D is strictly greater than A. Now the path difference between R1 and R2 is half into lambda. Now we can generate an equation sin theta equal to xy divided by zx. After some calculation, we can solve the equation and get a new equation, which is s sin theta equal to lambda. This is the condition for the first minima. To calculate higher order minima, we have to divide the slit accordingly. For the second minima, split the slit into 4 zones, which of width a by 4. And after some similar calculation, we will have s sin theta equal to 2 lambda. This is second order minima. Thus, for all the minima, we can generate an equation s sin theta equal to m lambda, where m is 1, 2, 3, 4, etc. Now I will talk about the intensity in single slit diffraction. From the analysis of single slit diffraction, we can consider light coming from the different parts of the same slit. According to Huygens principle, every part of the wavefront in the slit emits wavelets. These are like rays that start out in phase and head in all directions. Assuming the screen is very far away compared with the size of the slit, rays heading toward a common destination are nearly parallel. When they travel straight ahead, they remain in phase and the central maximum is obtained. However, when rays travel at angle theta related to the original direction of the beam, each travel a different distance to a common location, and they can arrive in or out of the phase. The ray from the bottom travels a distance of one wavelength lambda further than the ray from the top. Thus, a ray from the central travels a distance lambda by 2 further than the one on the left, arrives out of the phase, and interferes destructively. A ray from the slightly above the center and one from the slightly above the bottom will also cancel one another. In fact, each ray from the slit will have another to interfere destructively, and a minimum is intensity will occur at this angle. There will be another minimum at the same angle to the right of the incident direction of the light. The light passing through a single slit is diffracted in all directions and may interfere constructively or destructively depending on the angle. The difference in path length for rays from either side of the slit is seen to be d sine theta. At the larger angle, the path length differ by 3 lambda by 2 for rays from the top and the bottom of the slit. One ray travels a distance lambda different from the ray from the bottom and arrives the phase, interfering constructively. Two rays, each from slightly above those two, will also act constructively. Most rays from the slit will have another to interfere with constructively, and the maximum in intensity will occur at this angle. However, all rays do not interfere constructively for this situation, so in the maximum is not as intense as the central maximum. Finally, the angle shown is large enough to produce a second minimum. The difference in path length for rays from either side of the slit is d sine theta, and we see that destructive minimum is obtained when the distance is in an integral multiple of the wavelength. Thus, wavelength destructive interference for a single slit d sine theta equal to m lambda, where m is 1, minus 1, 2, minus 2, 3, etc. The d is the slit width, lambda is the light's wavelength, theta is the angle relative to the original direction of the light, and m is the order of minimum. Now I would like to request Koron to proceed with next topic. Thank you.
Adab sir, my name is Koron Chowdhury. My ID is 221115105. I am going to talk about double slit diffraction. So what is double slit diffraction? Double slit diffraction definition refers to an experiment in which light is permitted to diffract through slits that produce fringes or wave-like interference patterns on an opposite screen. In other words, double slit diffraction is the observed outcome where light passing through the two slits produces beams that interact with each other. In single slit diffraction, light outstretches in a line perpendicular to the slit, but in double slit diffraction, light diffracts when passing through the slits. But the light from those then interferes and produces an interference pattern on the screen. This is the double slit diffraction pattern differences between single and double slits. Some of the diffracted lights interfere constructively. They are bright spots and they are called maxima. And some of the diffracted lights interfere destructively. They are dark spots and they are called minima. The equation for the maxima is d sine theta equal to m lambda, where d is the difference of length between two slits, theta is the angle between two slits, m is maxima, and lambda is the difference between R1 and R2. Diffraction grating is similar to double slit arrangement. The slits are known as the rulings. Ruling number could be several thousands or millimeters per millimeters. A diffraction grating is an optical element that divides light composed of lots of different wavelength into light components by wavelength. The simplest type of grating is one with a large number of evenly spaced parallel slits. The separation between two adjacent ruling is grating spacing d equal to w by n. Here w width of the grating, n equal to total number of ruling. We know the angle of diffraction depends on the wavelength of the light used. To determine unknown wavelength, there is an equation where theta is equal to sine inverse m lambda by d. Thank you. From now on, Prohor is going to continue.
Adab sir, my name is Prohor Paul. My ID is 221115106. Now I will talk about X-ray diffraction. X-ray diffraction or XRD is a technique for analyzing the atomic or molecular structure of materials. It is non-destructive or works most effectively with materials that are wholly or partially crystallized. The technique is often known as X-ray powder diffraction because the material being analyzed typically is finely grounded down to a uniform state. Diffraction is when light bends slightly as it passes around the edge of an object or encounters an object or aperture. The degree to which it occurs depends on the relative size of an wavelength compressed to the dimension of the object or aperture it encounters. A crystalline solid, which consists of a regular array of atoms, might form a natural three-dimensional diffraction grating for X-rays. The idea is that in a crystal such as sodium chloride, a basic unit of atoms repeats itself throughout the array. When an X-ray beam enters a crystal such as sodium chloride, X-rays are scattered, that is redirected in all directions by the crystal structure. In some direction, the scattered wave undergo destructive interference, resulting in an intensity minimum. In other direction, the interference is constructive, resulting in intensity maxima. Figure shows three reflecting planes with interplanar spacing d, from which the incident rays shown are said to reflect. Rays 1, 2 and 3 reflect from the first, second and third planes respectively. At each reflection and the angle of an incidence and the angle of reflection are represented with theta. These angles defined relative to the surface of the reflecting plane rather than a normal to the surface. After they reflected, they must again be in phase because the reflection and the reflecting planes have been defined slowly to explain the intensity maxima in the diffraction of X-rays by a crystal. For these rays to be in phase, the path length difference must be equal to an integer multiple of the wavelength lambda of the X-rays. We find that the path length difference is 2d sin theta. In fact, this is true for any pair of adjacent planes in the family of planes represented in the figure. Thus, we have as the situation for intensity maxima for X-ray diffraction equals to 2d sin theta equals to m lambda. For m equals to 1, 2, 3 and continues. Call this Bragg's law, where m is the order number of an intensity maxima. Thank you. Thank you from Group 8. And the members of Group 8 are Nowshin Ahmed, Nayeeb Qureshi, Koron Chowdhury, and Prohor Paul.